Hello, my name is Sergiy Popov. I represent Kharkiv National University of Radio Electronics. Today I am presenting the paper Adaptive Neo-Fuzzy Bagging Metamodel and its Fast Learning. As you all know, bagging involves several models that are performing the same task working in parallel and producing independent solutions which are then combined in some manner to obtain the final output, which should be more accurate and stable than the outputs of separate models. There are several approaches to combining models' outputs. Voting is primarily used in classification tasks. Averaging is common for regression tasks. More advanced approach involves a metamodel that weights each model's output, defining its contribution to the output signal. In this research, we are focusing on improving the combining part of the bagging procedure. Standard bagging works in offline mode. That is, the whole dataset is available. Batch learning algorithms are used to estimate the fixed set of weights associated with the models. This also implies that a linear combination of models' outputs is performed. Our approach works in online mode when data is received and processed incrementally as a stream. That is, each sample is processed sequentially and only once. Therefore, online learning algorithms are employed that continuously adapt the weights. And the most important, we add nonlinearity to the metamodel using the neo-fuzzy approach. The metamodel architecture is shown on slide 4. It has a traditional linear part with the corresponding weights WP star, but each input signal is first preprocessed by the corresponding nonlinear synapse, marked as NSP, which performs the nonlinear F-transform. The structure of a nonlinear synapse is shown on the right side of the slide. The input signal in a nonlinear synapse is passed through a set of fuzzy membership functions UL, which introduce nonlinearity and corresponding tuned weights WLP, and then combined to form the output signal UP. The following formulas describe the metamodel's functioning in more detail. Equation 1 describes the linear part of the metamodel subject to constraints 2. Nonlinear synapse is processing data according to equation 3, which is a weighted sum of fuzzy membership functions applied to the input signal. In general, different types of membership functions can be used here, but usually simple triangular-shaped functions are described by equation 4. Here, CL are membership function centers that can be distributed uniformly in the input space or defined by some clustering procedures. The weights of the linear part of the metamodel are adjusted according to the local quadratic criterion 5. Due to the unbiased constraints imposed on the weights, optimization is performed by searching for the saddle point of the Lagrange function 6. This leads to a modified gradient procedure 7, which turns into standard stochastic gradient descent when lambda is equal to 0. Learning rate optimization leads to algorithm 8, which coincides with the Woodrow-Hoff learning algorithm in case of lambda equal to 0. The nonlinear synapse learning is also based on the local quadratic criterion 9. If we introduced combined vectors W and mu star, the metamodel output can be rewritten as formula 10. And then the optimal Catch-Match-Woodrow-Hoff algorithm can be used for the nonlinear synapse parameters tuning. To introduce additional smoothing properties, the modified procedure 12 can be employed. To validate our theoretical results, we performed a simulation based on the short-term electric load forecasting problem, specifically one-step ahead forecasting of daily electric load of one of the regional power systems of Ukraine. The regional series shown on slide 11 contains 337 samples and has several trends corresponding to different seasons, periodic patterns, sudden changes, and outliers. Because electric load in large systems depends on many external factors, some of which have true random or chaotic nature, like weather conditions, the time series is essentially non-stationary and noisy. This makes it forecasting a challenging task. And it is exactly the case when Bayesian methods can attempt to improve overall forecasting accuracy and stability by combining outputs from several models in the ensemble. As we work in online mode, the time series is processed sequentially as a data stream by 6 independent forecasting computational intelligence models whose outputs are shown as dotted color lines in this slide. It is evident that no one model is superior to the others for the whole series. We apply the proposed nonlinear metamodel and algorithm to obtain an optimal combination y hat star of the 6 forecasts from the ensemble member models. Error comparison in the table shows that the metamodel produces the error 1.44 times lower than the lowest error provided by the best ensemble member alone. So in this research, we considered the problem of an online optimal combining of models' outputs and proposed a new adaptive nonlinear neo-fuzzy Bayesian metamodel and fast online learning procedures for its tuning. Simulation showed promising numerical results and provided insights into ways of further improvement, one of which is fine-tuning of the nonlinear synopsis parameters, that is, number of membership functions and their centers distribution. We are moving forward with this research. Thank you very much for your attention.